Hello? Up? Yep. Ooh, okay. It's the middle of my talk. So, you'll see it in reverse first. I'm Susan Clark. I'm a fourth-year grad student at Columbia University, working with both Josh and Mary Putman for my thesis. And in this talk, I'm going to zoom in on just one feature of Josh's beautiful movie that he showed. And that is that this GALFA-H1 data is largely organized into these beautiful diffuse atomic fibers, these linear structures that sort of stretch across the sky. This is cutting in and out. So much of this work actually traces back to early work by Carl and Dick and others who showed that the orientation of starlight polarization on the sky traces large-scale H1 structures. So you can see that the little polarization pseudovectors in this plot follow the orientation of the galactic plane and also trace out some of the large-scale H1 structures we know and love, like loop 1. And in our work with the GALFA-H1 survey, we wanted to ask on a much smaller scale whether these diffuse atomic fibers are associated with the orientation of the magnetic field. So to do this, we needed a way to quantify the orientation of H1 as it moves and changes across the sky. So our answer to this is called the rolling Hough transform, or RHT for short. And this code is open source. You can go try it out for yourself and feel free to get in touch with me if you have questions. But essentially what we do with this is quantify the orientation of image data as a function of angle on the sky. So in this little cartoon, you can see what we're doing with our H1 data. First, we smooth and unsharp mask our data so that we're just working with a bit mask. So in the left-hand panel of this cartoon, the black represents ones and the white represents zeros. And we quantify linear intensity as a function of theta by sweeping out. So for every possible line that passes through the center of this little circular window, we calculate the fraction of pixels that are lit in the bit mask. And then we keep only the data that are above a certain intensity threshold. So for the center pixel of this circular window, the data that we retain is this purple line, this intensity as a function of theta. And what this means is that after we roll our circular window across a huge section of the H1 sky, we end up mapping 2 image dimensions to 3, where we're storing this linear intensity as a function of angle for every pixel in our image. And what we did with this is sample the RHT of the GALFA-H1 survey around a bunch of the starlight polarization measures in the Heiles 2000 catalog. And so this work was published in 2014, and what I'm showing here is this intensity as a function of theta sampled around 351 stars in a 1,300 square degree section of the high latitude GALFA-H1 sky. And I'm plotting this intensity relative to the starlight polarization measure around which we sampled it. So perfect alignment here between the starlight polarization and the H1 is at 0. An orthogonal orientation would be at pi/2, or equivalently minus pi/2. Remember, we can only get orientation in that direction from starlight polarization measures. So you can see that clearly these H1 fibers are very well aligned with the interstellar magnetic field as probed by starlight polarization. And we went on to do this also with a big swath of the Parkes gas survey in the southern sky. So in the right-hand panel is the same sort of diagram for all of the gas at least 30 degrees off the plane in the Parkes gas survey. And that survey is at a lower resolution than the GALFA-H1 survey. And what we found is that although there's clearly still a correlation between the orientation of H1 structures in the Park survey and this Heiles 2000 catalog of starlight polarization measures, the correlation is not nearly as tight, and we attribute this to the difference in resolution between the two H1 surveys. Meaning that what we're saying is that elongation along the orientation of the magnetic field appears to be a pervasive feature of the cold neutral medium, but it's not a scale-independent feature of the ISM, and this alignment will be degraded when you go to lower resolution. Somewhere along the way, of course, the Planck collaboration released this amazing all-sky 353 gigahertz dust polarization maps. And so rather than sampling around individual stars, we could now compare point estimates of the H1 orientation from the RHT with basically pixel by pixel at some resolution with the Planck data. And when we did this, we found an even more striking alignment between the GALFA-H1 structures and the orientation of the magnetic field on the plane of the sky. So this image, which Naomi gave you a sneak peek of, is a line integral convolution image. So what you're seeing is the convolution of noise with some vector field, or an orientation field in this case. So in the top panel, you're seeing the orientation of the neutral hydrogen in the GALFA-H1 survey as measured by our RHT. And in the bottom, you're seeing the magnetic field orientation as measured by Planck. And then overplotted, again, are these little white pseudovectors that show you the Heiles 2000 starlight polarization stars. And even by eye, you see this beautiful, pervasive correlation. And in fact, the coupling between the orientation of the magnetic field and the orientation of the H1 is so strong that we realized that we could use this to make inroads with another community. So this is showing you cross correlations between the RHT orientation, 353 gigahertz angles, and the starlight polarization angles, all, of course, at a common resolution. And of course, to us, the ISM is this beautiful thing worth studying in its own right, and we all love it. But if you're a cosmologist who, for example, might want to look for primordial polarization in the cosmic microwave background, you would really rather that the ISM not be there. And so we are going to use this very tight correlation to better constrain the plane of sky magnetic field orientation. Not only because we think that that's very interesting, but also because cosmologists can potentially use this to better clean out their foregrounds in their polarization data. So here I'm showing you some preliminary work where we're using the orientation of H1 as a prior on the orientation of the plane of sky magnetic field angle. And we can potentially create these higher fidelity maps of the magnetized foreground. So stay tuned for that. So this alignment between H1 fibers and the magnetic field is something that was, at least with this level of precision and quantification, previously unknown. And we're using the empirical result to facilitate some very cool science. But we still want to know why. Why is this the texture of the ISM? Why is it organized into these fibers? And as people in this room can tell you, in the diffuse ISM and beyond, there are myriad ways to create linear structure in the ISM. And in order for us to do one of Carl's favorite things, which is to have observation confront theory, I think it's already clear that we're going to need observationally to go beyond the morphological fact of linear structures. And we're even going to need to push beyond quantifying the orientation between these structures and the interstellar magnetic field. So I'm going to give you a sneak peek of some of the ways that we are trying to observationally measure more properties of these diffuse atomic fibers to hopefully one day confront theory. So one question that's been raised is whether these fibers are physically isolated in 3D space, whether they're fundamentally filamentary, or whether perhaps they are overdensities that we're seeing because they're sort of wrinkles in a more sheet-like medium. So these are actually just pieces of paper that were crumpled up and photographed in Hester 1987. But more recently, for specifically the type of H1 fibers that we've been looking at, it's been proposed by Calabarella et al. And some others that what we're seeing really are crumpled sheets. And one of the ways that we would like to examine this question more closely is by looking at multi-wavelength data. So we see these fibers spatially coincident, not just in the GALFA-H1 and dust surveys like Planck, but also, for example, in the WISE 12 micron data. And we're hoping to compare properties of all these different data sets to get a better sense of whether these are physically isolated structures or whether we're seeing these edge-on sheets. So one morphological telltale sign that something that you're looking at is a sheet might be something like a cusp, where you sort of are seeing the edge of a wrinkle in your sheet. And there are places in the H1 fibers and in these other media where that might be what we're seeing. But we can also look at properties like the dust-to-gas ratio, which is what I'm showing in the third panel here, and see that, for example, in this cusp, there's an enhanced dust-to-gas ratio, which is not necessarily what you would expect if this is all just wrinkles in what is actually a smooth medium. So this is something that we're planning to dig into further and would love to talk to people here about. We can also, of course, look at the velocity structure of our H1 fibers. And just very preliminarily, we're not seeing that they, for the most part, have coherent flows along them, although we can find cases where that does exist. But we can look for things like coherent velocity gradients and try and get a better sense of that. I should also mention that there's been a lot of interest lately in physical widths of things like H1 fibers and other filamentary structures. And we've actually just obtained some VLA data to look at a fiber more closely and hopefully get a sense of what the physical widths of these fibers might be past the resolution of GALFA-H1. So this is all stuff that we would like to talk to theorists in the room and other observers about and see what can be most useful for the community as we try to determine why the texture of the ISM is what it is. And just a very brief plug, my theoretical work lately has actually focused on the magnetorotational instability. So if there's anyone here who would also like to discuss analytic studies of MRI saturation, I would also like you to seek me out for that. So we've quantified an alignment between H1 fibers and the interstellar magnetic field, both using starlight polarization measures and the Planck polarized dust emission. And we're currently using this alignment to create higher fidelity maps of the plane of sky magnetic field, both for ISM studies and for CMB polarized foreground purposes. So we're continuing to study the properties of these H1 fibers, and we hope you'll stay tuned. Thank you.
Questions, a lot of questions, a lot of hands. So let's start from over here first.
It's great stuff. I love this stuff.
Oh, you're not.
There we go. Do you have a preferred, like talking about your new stuff, the crumpled sheets and things, do you have a preferred situation that is creating these fibrous structures with respect to what the magnetic field looks like? Basically, you see magnetic field along the structures. Is there some physical reality that would make more sense with the fields being along it? Do they have to be little needles, or would crumpled sheets make more sense with the fields being parallel?
Yeah, part of the point is that the alignment with the magnetic field alone can't distinguish between those two scenarios. So we need to move to other sorts of observations, like maybe dust to gas ratios, because both are consistent with that, essentially. Yeah.
Okay, Alex and then Chris.
What is the change of alignment of the structures with magnetic field as you change the threshold?
You mean density threshold?
Yes.
Well, we are mostly looking at very diffuse gas here. Actually, that dust to gas ratio I showed is one of the first places we've made connections between the atomic and the molecular H1, or hydrogen.
So you were not changing the threshold and seeing whether you change the correlation?
No, but that has been done with Planck data. I'm sure someone here will talk about that. But you do see generically a turnover where things begin as largely parallel in the diffuse media, and as you move to higher densities, either they lose a preferred correlation or they're anti-aligned, perpendicular to the magnetic field.
Whether with the same data, not going from the place to place, just change the threshold, and whether you will change the alignment with the threshold.
Yeah, so that's been found on the Planck data.
Yeah, my question is, you had the very interesting result that the dust to gas ratio in these fibers seems to be different. And my question is, if they are edge on sheets, which makes a lot of sense to me, then could it be that it's because of optical depth in the 21 centimeter line? It would mean that it would be a systematic effect then that in the sheets you would have a higher dust to gas ratio because the gas, you're not seeing all the gas.
Yeah, no, that's right. We need to look at more than just this one example, I'd say, to determine whether that's the case, but maybe.
Okay, last question, Don Cox.
So I was holding those window screens when the photographs were being made by Jeff Hester. They were window screens, so they had a pattern in them that was crisscrossed. And it seems to me that once you crumple it, if you take either one of those orientations of the strings to be the magnetic field, it's very unlikely that the field would follow the crumples. I'm not saying that very well, I think, but the field could be going this way, and you crumple it that way, and you get your lines of stuff looking like this, but the field would still be going that way.
Oh, I think I understand what you're saying. Although, with all these observations, we have to remember we're only seeing the plane of sky component of the magnetic field. So that's the only thing that actually has to be aligned.
But in the plane of the sky, it would still be going, could be going crossways. That's all I'm trying to say.
All right, we'll have to talk about this more.
It's definitely time to continue conversation over coffee. Let's thank Susan again, please.